Welcome to This Explainer. Okay, imagine this. Your application goes viral overnight. It's literally the dream, right? Millions of users are flooding in to use this amazing thing you've built. That is, until your single, highly expensive database node practically catches on fire under the immense load. You can't just keep upgrading to a bigger machine forever. So today, we're going to map out the solution to that exact problem. We are diving into the fundamental concept of database sharding, or what we like to call the architecture of infinite scale. Here's a quick roadmap for today. We'll be hitting the basics of sharding, multi-tenancy, key range versus hash partitioning, how to handle skewed hotspots, request routing, and finally, the ultimate headache, secondary indexes. Let's get into it.
Section 1. The basics of sharding.
So picture this. A single machine just cannot handle your data volume or write throughput anymore. And you can't just keep buying a bigger, more expensive server. Eventually you hit a physical ceiling. There's just no way around it. Instead, you have to split your data into smaller, manageable, totally independent databases called shards. Think of it like replacing one massive, super crowded filing cabinet with a dozen smaller ones, so multiple people can actually search through them at the exact same time. Each shard is its own tiny database, but together they form this one massive, logical system.
But there's always a catch, right? Here is the immediate trade-off. On one hand, we unlock what is effectively infinite horizontal scale, using standard, everyday cloud hardware. We can distribute our system across multiple data centers and handle pretty much any level of traffic you throw at it. But on the other hand, we pay a really hefty tax in system complexity. You have to explicitly decide exactly how to partition your data. And if you need a transaction to cross multiple shards, well, you suddenly have to rely on incredibly expensive distributed coordination just to keep everything consistent.
Section 2. Sharding for multi-tenancy.
In the real world, honestly, this concept is an absolute lifesaver for software as a service products. Giving each enterprise customer their own dedicated shard achieves true resource isolation, meaning if one tenant runs a terrible, massively heavy query, it doesn't crash the system for anyone else. It's also fantastic for things like regulatory compliance, think GDPR, because a user's data is safely contained in one isolated box. But the puzzle then becomes, how on earth do you manage the overhead of thousands of tiny tenants? And what happens when one massive enterprise customer completely outgrows their single shard?
Section 3. Key range versus hash sharding.
All right, think of an old-school multi-volume print encyclopedia. This is actually the perfect analogy for key range sharding. If you're looking for a word that starts with B, you don't go searching through the whole library, right? You just grab volume 1. In a database, we assign a continuous, alphabetical, or maybe chronological range of partition keys to a specific shard. It sounds super simple. Your data is logically grouped, making it incredibly easy to find contiguous information without jumping all over the place between different servers.
Now, while this setup allows for some really efficient range queries, like say your key is a timestamp, you can instantly fetch all the sensor readings for a specific month from just one single node. There is a pretty fatal complication here. If your application is constantly writing current data, well, all those new writes are hitting the exact same timestamp range. That means everyone is writing to the exact same node, practically pushing it to the brink of failure, while the rest of your super expensive cluster is just sitting there completely idle.
So how do we fix that? Well, we turn to hash sharding. Instead of grouping data logically, we run the partition key through a mathematical hash function. Those consecutive timestamps, they get magically transformed into widely scattered, completely random-looking numbers. Then, we just assign a range of these hash values to each shard. The underlying data hasn't changed at all, but its physical placement in our cluster is now dictated by this algorithm, smoothing out all that traffic perfectly. The upside here? We've totally solved the load distribution problem. Skewed data is now perfectly, beautifully balanced across all nodes. But the downside? We've completely destroyed the ordering of our keys. So if you want to run a simple report for, say, all users who signed up last week, you can't just check one shard anymore. No way. You actually have to broadcast that query across every single shard in your entire system, which, as you can guess, can severely impact performance when you're dealing with massive datasets.
Moving on to Section 4, skew and hotspots.
But wait, even hash sharding has an Achilles heel, the dreaded hotkey. Imagine a massive celebrity post on a social network and literally millions of people react simultaneously. Because all those interactions are tied to the exact same partition key, which is the ID of that specific post, they all hash to the exact same shard. So despite our beautiful mathematical hashing, one machine still gets completely crushed under a massive tidal wave of traffic.
To survive a wave like that, engineers have to build specific workarounds. You might build a system that dynamically detects a celebrity key and then immediately isolates it on a dedicated, highly expensive supernode. Or, here's a neat trick, you can have the application append a random 2-digit number to the very end of the hotkey. This actually forces the database to view it as 100 different keys, successfully splintering that celebrity's massive load across the entire cluster. Sure, it takes extra work to read it back, but it absolutely saves your system from going down.
Section 5. Request routing strategies.
Okay, so with our data now scattered across hundreds of nodes, how does a client application actually find the data it needs? We basically have 3 main choices here. Option 1, a client contacts any random node, and that node just politely forwards the request if it doesn't have the data. Option 2, we insert a dedicated routing tier, like a shard-aware load balancer, that directs all the traffic. Or option 3, we make the client applications themselves shard-aware, which cuts out the middleman entirely so they connect directly to the right database.
But remember, shards aren't static. They're constantly being moved around to balance load. So how do these routing tiers keep up with all that movement? To prevent total chaos, or a terrifying split-brain scenario where 2 nodes both think they own the same data, systems rely on a highly consistent coordination service like Zookeeper. Think of it as the ultimate, unarguable source of truth. It tracks exactly who owns what, and it instantly alerts the routing tier the very millisecond anything changes. Section 6. Handling secondary indexes.
Finally, we arrive at arguably the biggest headache in distributed databases, secondary indexes. If you want to search a database by anything other than its primary partition key, let's say finding all users who drive a red car, you face a pretty brutal choice. You can use local secondary indexes, where each shard maintains its own mini-index. Writes here are super fast, but reads require a notoriously inefficient process called scatter-gather, where you basically have to beg every single shard for answers and then combine them. Alternatively, you can build a global secondary index. This makes reading blazing fast, but every single time you update a record, you have to execute a really painful, coordinated update across the network to a completely different node.
So what does this all mean for us? Sharding absolutely solves the ultimate growth problem. It shatters the physical limits of single machine hardware. But as we've explored today, it's definitely not free magic. It introduces an entirely new universe of engineering puzzles, from mitigating those viral hotspots to coordinating routing tiers to managing those tricky scatter-gather indexes. The architecture of infinite scale is incredibly powerful, but you really have to ask yourself, is your application truly ready to pay the sharding tax? Definitely something to think about as you design your next system.